Let's look at the review exercises for Chapter 3. Number 1, if the probability of A is 0.3, the probability of B is 0.4, and the probability of A and B is 0.2, find the probability of A or B. Now remember, we know that the probability of A or B is the probability of A plus the probability of B minus the probability of A and B. And since we know that the probability of A is 0.3, the probability of B is 0.4, and the probability of A and B is 0.2, the answer is simply 0.3 plus 0.4 minus 0.2, which is 0.5. Number 2. Suppose you ask a friend to randomly choose an integer between 1 and 10 inclusive. What is the probability that the number will be more than 5 or odd, and enter your probability as a fraction? First of all, we're looking at the numbers 1 through 10, or the integers 1 through 10. We want to know the probability that the number will be more than 5. That would be 6, 7, 8, 9, 10. Or odd, which would be 1, 3, 5, 7, 9. Taken all together, if you count everything that you've indicated, that's 1, 2, 3, 4, 5, 6, 7, 8. That's 8 out of 10, which can be reduced to 4/5. Number 3, use the data in the table below, which shows the employment status of individuals in a particular town by age group. So we're given a table with a column for the age groups, a column for the number of full-time, the number of part-time, the number of unemployed. The question is, if a person is randomly chosen from the town's population, what is the probability that the person is under 18 or employed part-time? So the strategy here is to look at the table and identify the number of people who are under 18. That would be the first row of the table. So 24 full-time, 176 part-time, and 372 unemployed. And then look at the ones that are employed part-time. That would be the middle column. And now we want to do the probability that the person's under 18 or employed part-time. So we simply need to count every number that we circled because it's an or. If it were and, we would just look at the overlap. But this is or, so we count every number that's circled. So the probability that a person chosen at random from this town's population is under 18 or employed part-time is the number of ways that can happen, which again is the sum of all those numbers circled, divided by the number of possible ways that a person could be chosen under any circumstances, and that's just the sum of every number in that table, which, because they don't tell us, we have to actually add up. Sometimes they'll tell us that so that we don't have to add, but here we do, and you end up with 1,178 divided by 3,418. That happens to reduce to 589 over 1709, but WebAssign really doesn't mind if you don't reduce that fraction. So you could put in 1178 over 3418 and get the right answer. What you can't do is change it to a decimal and give an approximation unless they ask you to do it that way. Number 4, use the formula for the probability of the complement of event. 2 dice are tossed. What is the probability of not getting a sum of 9? And enter your probability as a fraction. So if you remember when we roll 2 dice, my recommendation is you make this 2-by-2 table showing each of the 36 possible outcomes. Now if we're looking at getting a 9, if you look in that table, 6, 3, 5, 4, 4, 5, and 3, 6 are the only combinations of die rolls that give you a sum of 9. So there are 4 of those, and there are 36 possibilities when you roll 2 dice. So the probability of getting a sum of 9 is 436, which if you reduce it is 1/9. But keep in mind, they ask you what the probability of not getting a sum of 9. So the complement rule, which is what they ask you to use, says the probability of not getting 9 is 1 minus the probability of getting 9. If the probability of getting that sum of 9 is 1/9, then the probability that you don't get that sum would be 1 minus 1/9, which is 8/9. I would say keep in mind, even though they told you to do it by the complement rule, you'll still get the right answer if you just count directly. You could say, well, if there are 4 ways of getting a 9 and there are 36 possibilities, there are really 32 ways of not getting a 9 as a sum. So it would be 32 over 36, which is 8/9, and you could get the answer directly. So even though they ask you to do it by the complement rule, you certainly could do it just by counting directly. Number 5. Use the formula for the probability of the complement of event. Same instructions as the previous problem. A single card is drawn from a deck. What is the probability of not drawing an ace? Well, remember, there are 52 cards in the deck. There are 44 cards that are not aces and 4 cards that are aces. So if I'm looking at the probability of something to do with aces, or not aces in this case, I want to partition the deck of cards into aces and non-aces. So I have 4 aces and 48 non-aces. That means the probability of not drawing an ace is 48 over 52. Notice they actually asked me to do it by the complement rule, and I didn't. It's just faster to do it this way. If you want to do it by the complement rule, you would take the probability of getting an ace is 4 out of 52, and you would say 1 minus that, and you'd get still 48 50-seconds. You get the same answer. In either case, 48 50-seconds does reduce to 12/13, but WebAssign does not force you to reduce the fraction. But what you can't do is write it as an approximated decimal, unless they tell you that in the directions. Number 6. A magician shuffles a standard deck of playing cards and allows an audience member to pull out a card, look at it, and replace it in the deck. 2 additional people do the same, so a total of 3 people. Find the probability that of the 3 cards drawn, at least one is a face card, and round your answer to 1 decimal place. And our answer is going to be given as a percent. So first of all, we're drawing 3 cards. We're drawing with replacement because it says once we draw it, we replace it in the deck. We just observe what we get, but then we put it back in the deck. And of course, reshuffle. We've talked about this before, but when you're asked to find the probability of at least one, the best way is to find out the probability that something doesn't happen and use the complement rule to say 1 minus that probability is the probability that you get at least 1. So the probability of getting no face cards can be calculated by the multiplication principle, which says, in this case, that the probability of getting no face cards on the first draw times the probability of getting no face cards on the second draw times the probability of getting no face cards on the third draw is the probability of getting no face cards at all. So what is the probability of getting no face cards on the first draw? Well, remember, there are 52 cards, 12 face cards. The rest of them, which would be 40, are not face cards. So if you're not going to get a face card on the first draw, that means you're drawing from the 40 cards that are not face cards. So that's 40 out of 52. Since you're drawing with replacement, you're putting that card back in, so it's 40 out of 52 the next time you try it, and it's 40 out of 52 the third time you try it. If it were without replacement, it would go 40, 39, 38. But because it is with replacement, the 40 stays 40 because you're putting the card back in. In any case, the probability of getting no face cards is 40 50-seconds times 40 50-seconds times 40 50-seconds. And the probability of getting at least 1 face card is 1 minus that product. Now 40 50-seconds times 40 50-seconds times 40 50-seconds, because they ask you to round your answer to 1 decimal place, at any point in this process you can go ahead and change things to decimals and start working with decimals. Had they not asked you to approximate, you would have to leave it fractions. I'm going to leave it fractions a little longer, but you don't have to. At any point you feel like turning things into decimals, you can go ahead and do it. What I did is notice that 40 50-seconds is the same as 10/13, and I just wrote it as 10/13 times 10/13 times 10/13. So it's 1 minus the product of 10/13 times 10/13 times 10/13, which is 1,000 over 2197. So you get 1 minus 1,000 over 2197. And at that point, I went ahead and took 1,000 divided by 2197 and turned it into a decimal. They want you to round your final answer to 1 decimal places, but when you're doing intermediate steps, always take more decimal places than they want for the final answer. In any case, you get 1 minus 0.455166 approximately, which comes out to be about 0.5448. And now they say round it, but they also say write it as a percent. So you got to be careful here. You don't round it before you change it to a percent. So your first thought is, well, they told me to take 0.5448 and round it to 1 decimal place. But if you glance back up there, they said the answer should be a percent. So what they're asking you to do is round the answer, which is a percent, to 1 decimal place. So you have to round after you've changed it to a percent. So if you move the decimal place 2 places to the right, you get 54.48%. And if you round that off to one decimal place, that would round off to 54.5%. Number 7. Compute the conditional probabilities, the probability of A given B and the probability of B given A, and round your answers to 3 decimal places. The probability of A is 0.6, the probability of B is 0.1, and the probability of A and B is 0.03. Now, there are formulas for this. I'm going to show you the way I do it so I don't have to memorize these conditional probability formulas, but I'll show you at the end how you could do it if you wanted to actually memorize the formulas. What I use is a tree diagram. So that probability, if you look at it in terms of A followed by B, the first branch going to A is the probability of A, and then the probability going from A to B is the probability of B given that A has occurred. The product down that branch is the probability of A and B. So we talked about this before. When you multiply down a branch of a tree diagram when you're doing these probabilities, you get an AND. So the probability of A times the probability of B given A is the probability of A and B. And because I know the probability of A is 0.6 and I know the probability of A and B is 0.03, I get an equation that says that 0.6 times whatever the probability of B given A is equal to 0.03. And if I divide both sides by 0.6, I get 0.05. So the probability of B given A is 0.05. Now if I want to do the probability of A given B, I draw a tree diagram where B comes before A. So I run down the first branch to B, that's the probability of B. But the second branch is the probability of A given that B has already occurred. And again, when you multiply down a branch, that's like doing an AND. So the probability of B times the probability of A given B is the probability of A and B. And I know that the probability of B is 0.1. I was given that. I know the probability of A and B is 0.03. I was given that. So I know that 0.1 times whatever the probability of A given B is equal to 0.03. So if I divide both sides of that equation by 0.1, do the arithmetic, I find out that the probability of A given B is 0.3 or 0.3. It says to round your answers to 3 decimal places, so I wrote 0.3 as 0.300. The software, when it solves zeros afterwards, might not require you to do that, but there's no harm in doing it. And the same thing with the second answer. I wrote 0.050 because it said 3 decimal places. I'm guessing that if you just wrote 0.05, it would accept that, since the 0 doesn't really change anything. But it asked for 3, I gave 3. I also said earlier that you could do it using the formulas. I don't like to memorize a formula if I can figure out a way to do it without the formula, but some people don't feel that way. If you did want to just memorize the formulas, remember that the probability of A given B is the probability of A and B divided by the probability of B, and the probability of B given A is the probability of A and B over the probability of A, and then you could plug the numbers in and you'd get it a little faster, but it requires you to have memorized those formulas. So you have your choice, whichever way you want to do it. I try to unload my memory and memorize as few formulas as possible, but it's up to you which way you want to do this. Number 8. Use the data in the table below, which shows the employment status of individuals in a particular town by age group. A person from the town is randomly selected. What is the probability that the individual is employed full-time given that he or she is between 18 and 49 years of age? So we have this chart. The columns are the employment status, either full-time, part-time, or unemployed, and the rows are the age groups. We're given that he or she is between 18 and 49 years old. Whenever you have a conditional probability, whatever you're given becomes your sample space. So if you're only interested in people between 18 and 49, you can completely eliminate the 0 through 17 row and the 50 plus row. So you're only interested in those 9 numbers in the middle 3 rows. That becomes the sample space. Given that reduced sample space, what is the probability that the individual is employed full-time? Well, full-time is the first column, and we're only looking at now the middle 3 rows, so the number of people that are employed full-time in the reduced sample space is 193 plus 348 plus 581. So the probability that a person chosen randomly from that town is full-time given that they're between 18 and 49 years old. It's just how many people in the reduced sample space from that chart are full-time divided by all 9 of those numbers added together. Remember, that's the new sample space given the information that you already know that the person is between 18 and 49 years old. So the probability is the number of things you want to get, which are full-time, divided by anything that's possible. And after you're using the condition, only those 9 numbers on the middle 3 rows are possible. So if you add all those things up, you'll get 1,122 over 1,865. They didn't say anything about rounding, so just put in your answer as a fraction. Number 9. Use the data in the following table, which shows the results of a survey of 2,000 gamers about their favorite home video game systems, organized by age group. If a survey participant is selected at random, determine the probability of the following and round to the nearest hundred. So this time we're rounding. The participant prefers Sega Genesis, given that the age group is 18 to 24. Well, if you look at the chart, the given that is the condition. We know that the person's between the age of 13 and 24. So that eliminates the 0 to 12 row, and it also eliminates the greater than or equal to 25 row. So we're only working with the middle 2 rows now. That's the reduced sample space. Given that, we want to calculate the probability that the person prefers Sega Genesis. In other words, the probability that they prefer Sega Genesis given that they're between 13 and 24 years of age. So that's the probability that the person likes or prefers Sega Genesis. That's the 89 plus 83 over the 8 numbers on those middle 2 rows, which is the sample space after you've taken the condition into account. And if you do the addition, you end up with 172 over 1177. But this time they wanted you to round to the nearest hundredth. So this time you take your calculator, you get about 0.146134. If you round that to the nearest hundredth, that would round up to about 0.15. Number 10. A snack-sized bag of M&M candies is open. Inside, there are 12 red candies, 12 blue, 7 green, 13 brown, 3 orange, and 10 yellow. 3 candies are pulled from the bag in succession without replacement. What is the probability that the first 2 candies drawn are brown and the third is green? So we're looking for brown, brown, green. Remember, there are 12 reds, 12 blues, 7 greens, 13 browns, 3 oranges, and 10 yellows. That's 57 if you add them all up. We're going to pull 3 candies without replacement. Without replacement. So the probability of the first one being brown times the probability of the second being brown times the probability of the third being green gives us the probability that we get the first 2 browns and the third green. Well, what is the probability the first is brown? Well, it's 13 out of 57. Now, you're drawing without replacement, so what's the probability the second one is brown? Well, you didn't put the brown one back in, so now you only have 56 total, and you took one of the browns, so there are only 12 browns left, so the probability that the second is brown is 12 out of 56. If you'd been drawing with replacement, it would have still been 13 out of 57, but we're not here. Now what's the probability the third one is green? Well, remember we've already drawn out 2 M&Ms by now. We started out with 57. We've drawn out 2, so there are only 55 M&Ms left. But we haven't drawn any green, so the probability of getting a green, there are still 7 there, so it would be 7 out of 55. And if you take the product, you get 13 57ths times 12 56 times 7 55ths, and that's 1,092 over 175,560. It doesn't say to round. WebAssign does not force you to reduce. If you do reduce, you'll get 13 over 2,090, but if you put in the unreduced fraction, you'll be okay. Number 11, a pair of dice are rolled twice or tossed twice. Find the probability that the first roll is a total of at least 10 and the second roll is a total of at least 3. Always, when you're doing these pair of dice problems, remember that you're going to be drawing your rectangular sample space, but also in this case, when you're rolling die, one toss is separate from the other toss. You're actually rolling a pair of dice twice. So you're rolling 2 pair of dice getting a result, then you're rolling 2 pair of dice again. Those are independent events. The probability of getting something on 1 pair of die roll does not affect the probability of getting it when you do it again. So 2 things. You're going to be using your sample space from a rectangular 6x6 rectangle, but you're also tossing a pair of dice twice, so you're going to be doing it twice, and those 2 events are independent because 1 die roll of 2 dice doesn't affect what happens when you do it again. We want to find the probability that the first roll is a total of at least 10. So again, if you draw out your sample space as a 6x6 rectangle, at least 10 means 10, 11, or 12. So if you count, you can see there are 3, 4, 5, 6. There are 6 rolls that are 10, 11, or 12, which is at least 10. So that probability is 6 out of 36. The probability that the first roll is at least a 10. We want the second roll to be at least 3. Well, if you look at the second roll, at least 3 means 3, 4, 5, 6, 7, 8, 9, 10, 11, or 12. And you can see there are 35. In other words, the only roll that's not at least 3 is the 1-1 roll, which is only 2. So 35 out of the 36 rolls are at least 3. So the probability that the first roll is at least 10 and the second roll is at least 3 is the product of those 2, which gives you 636 times 3536. If you want to do some reducing, you can. 636 reduces to 1/6. But anyway, when you multiply it out, you're going to end up with 35 over 216. They did not ask you to reduce it, so you need to enter your answer as a fraction. 12. A pharmaceutical company has developed a test for a rare disease that's present in 0.6% of the population. The test is 95% accurate in determining a positive result, and there's a 4% chance of a false positive. What is the probability that someone who tests positive actually has the disease? And when we get the answer, we want to round it to 2 decimal places. So, let D be the event that the person has a disease, and let T be the event that the test is positive. So capital D means the person has a disease. Capital T means that the person tested positive. I want to find the probability that the person has the disease given that that person tested positive. So that's the probability of D given T. So first of all, let's look at the event D. It's the event that the person has the disease, and the event T is the event that the person tests positive. So keep in mind that's what those 2 things mean. I like to use tree diagrams. It helps me visualize what's going on. So I'm going to use a tree diagram here. A person either has the disease or doesn't. So on the tree diagram, I start out with a branch going to D, meaning that person has a disease, and then I'm doing a branch for D prime or D complement, which is going to be the probability that the person does not have the disease. Given the person has a disease, they can still either test positive or not positive. So that T complement means the person didn't test positive. And then if the person doesn't have the disease, that person could still test positive or not. So that's your tree diagram. It goes D, D complement. If you go down the D branch, it could be T, T complement. If you go down the D complement branch, it could still be T or T complement. And having done that, I want to emphasize that first branch is whether the person does or doesn't have the disease. The second branch is whether they test positive or not. Because just because you test positive, there is a possibility that you tested positive and you didn't have the disease. There's a possibility that you test positive and you did. There's a possibility you test positive and you didn't. There's a possibility you don't have the disease but you do test positive. There's a possibility you don't have the disease and you don't test positive. And that's what the tree diagram does for you. It gives you every possibility in some kind of organized and visual way. Remember, we're given that the person tests positive. So if we already know that the person tests positive, we don't have to worry about the branches where the person tested negative. So we're only interested in a person that has the disease and tests positive, or the person didn't have the disease but still tested positive, because the conditional part said the person tested positive. That means that we can just forget about the other 2 branches. We're given that the person did test positive. So our sample space now is reduced to just 2 branches of that tree not all 4. Now from this point, just start off at the beginning. What is the probability that goes on the disease branch? Well, if you read the problem, it says 0.6% of the population has a disease. Now, when you want to change a percent to a decimal, you move the decimal 2 places to the left. So 0.6% is 0.006. And remember, the probability that you don't have the disease is 1 minus the probability that you do. So if the probability you have the disease is 0.006, then the probability you don't have the disease is 1 minus 0.006, which happens to be 0.994. Okay? Now you want to try to work down the other branches. That top branch, the second part of the top branch, is the probability that you have the disease and tested positive. Well, it says the test is 95% accurate, so there's a 95% chance, 0.95, that if you have the disease, you test positive. So the only other branch we don't have is the testing positive branch off of the case that you don't have the disease. Well, that's what we call a false positive. You don't have the disease, but the test said that you did. So we need to fill that out. You can also go ahead and multiply along the top branch before you do this other one if you want to. So I know that the probabilities along that top branch, when you multiply down a branch, you're doing an AND. So that probability down the branch is the probability you have the disease and you tested positive. And if you multiply those two decimals together, you get 0.0057. And as I said, the only place I don't have now is the branch off of the don't have the disease node, but I did test positive, or that person did test positive. That's called a false positive. If you don't have the disease but you test positive, that's called a false positive. There's a 4% chance. 4% is 0.04. And again, if you multiply down a branch, you're doing an AND. So the probability you don't have the disease and you test positive is 0.994 times 0.04, and that comes out to be 0.03976. Going back to your definition of conditional probability, the probability that you have the disease given that you test positive is the probability you have the disease and you test positive divided by the probability you test positive. Well, using that tree diagram, we can calculate all those things. The probability you test positive is just going to be the sum of those probabilities you've already calculated, because the first branch is part of the probability that you tested positive. That's if you have the disease and test positive. The other part of the probability that you test positive is the probability you didn't have the disease yet you test positive. So the sum of those two branch products is the probability you tested positive. That's the denominator. The numerator, the probability you have the disease and tested positive, is the top number, the 0.0057. So the probability you have the disease given that you tested positive is going to be 0.0057 divided by the sum of 0.0057 and 0.03976. And if you do the arithmetic, it comes out to be approximately 0.12538, which rounded to 2 decimal places would be 0.13, which is about 13%. Number 13. The outcomes of an experiment and the probability of each outcome are given in the table below. Compute the expectation for this experiment. This is the absolute simplest case of expectation, and you should hope to have a whole test full of problems like this. They gave you the outcome in a column in the table, and they gave you the probability of the outcome in another column. When you have it set up like that, all you have to do is multiply across each row. The outcome times the probability of the outcome, and then sum the results. So if you multiply across the rows, you get 0.4 times 5, which is 2.0. You get 0.2 times 6, which is 1.2. You get 0.2 times 7, which is 1.4. You get 0.08 times 8, which is 0.64. You get 0.07 times 9, which is 0.63. And you get 0.05 times 10, which is 0.5. And if you add them all up, you get 6.37, and that is the expectation for this experiment. If you're given the outcomes and their probabilities, that's the simplest case for calculating expected value or expectation. Number 14. One of the wagers in the game of roulette is to place a bet that the ball will land on a red number. 18 of the numbers are black, 18 are red, and 2 are green. If the ball lands on a red number, the player wins the amount of his bet. If a player bets $1, find that player's expectation and round your answer to 2 decimal places. So the first thing is to understand what they're saying. We want to place a bet on a red number, or we want to look at that probability at least. We know they're 18 black, they're 18 red, and they're 2 green. Now we only want to know whether it lands on a red or it doesn't. So from our point of view, we don't care about the black and the green separately. We only want to know if it's red or not. So we just add together the 18 black and the 2 green and think of them as 20 things that aren't red. So from our point of view, we want to partition those 3 colors into being just red and not red. So there are 18 reds, 20 non-reds. That's 38 altogether. Build yourself the table so you can calculate the expectation. The first column is the win-lose amounts, how much you win or lose. The second column is the probability of that happening. The first row is for landing on a red, if the ball lands on a red. The second row is the probability or the possibility that the ball lands on something that's not red. So you just take it one at a time. If the ball lands on a red number, the player is going to win the amount of his bet. So if a player bets $1 and the ball really does land on a red, that player wins $1. If that player does not win $1, the player loses the dollar, so that's negative $1. Now we need to calculate the probabilities and we're practically home free. Well, remember there are 18 reds out of 38, so the probability of that player winning $1 is 18 out of 38. The rest of the balls are not red, and there are 20 of those, so the probability that the player doesn't land on a red is 20 out of 38. And to calculate the expectation, you multiply across the rows and then add. So if you multiply 1 times 18 38ths, you get 18 38ths. And if you multiply negative 1 times 20 38ths, you get negative 20 38ths. And if you say 18 38ths minus 20 38ths, you get negative 2 38ths. They ask you to write that as a decimal rounded to 2 decimal places, so you have to divide. That comes out to 2 decimal places to be negative 0.05. So the expectation is negative 5 cents. On average, you'll lose about 5 cents every time you bet $1 on that game. Number 15. Many casinos have a game called the Big Six Money Wheel, which has 54 slots in which are displayed a joker, the casino logo, and various dollar amounts as shown in this table. Players may bet on the joker, the casino logo, or one or more dollar denominations. The wheel is spun, and if the wheel stops on the same place as the player's bet, the player wins that amount for each dollar bet. Notice the table has a denomination column and a number of slots column. The question is, if a player bets $3 on the $5 denomination, find the player's expectation and round your final answer to 2 decimal places. Notice that if you add up the number of slots, those numbers add up to the 54 slots that they told you in the beginning that there were. Those counts are going to be the basis of our probabilities. Notice that it said the player bets $3 on the $5 denomination. So that row that starts off $5 with the number of slots being 7 is the player's bet, and that player bet $3. So you want to build your table that's going to allow you to calculate the expectation. You need a column for the amount won or lost, and you need a column for the probability of that happening. And from this player's point of view, you're only interested in whether the wheel or the ball on the wheel stops on the $5 slot or not. So you need a row for the $5 slot landing and the probability that's going to be calculated there, and you need a row similarly for the lands on something else besides the $5 slot. So if there are 7 slots for the $5, that means if there are 54 in all, there are 54 minus 7. There must be 47 slots that don't provide a winner for that player's bet. It's a $3 bet. So if the player wins $5 for each dollar bet, that means with a $3 bet, that player wins 5 times 3 will win $15. On the other hand, if the player loses the player just loses the amount bet, which is $3. So it's a negative $3 loss. So the player stands to make $15 if the ball lands on the $5 slot, but stands to lose $3 otherwise. Now we just need the probabilities. Since there are 7 $5 slots and there are 54 in all, the probability that that ball lands on a $5 slot is 7/54, which means the rest of them, the 47, are not winners for that player. So there's 47/54 chance of that player losing $3. Once you get the table set up, you just multiply across and add down. So if you multiply 15 times 7/54, you get 105/54. And if you multiply negative 3 times 47/54, you get a negative 141/54. Notice that we're going to be rounding to decimal places, so if you really didn't want to work with the fractions, you could go ahead and change them to decimals now and get your decimals in earlier than I've done. But if you do that, make sure you carry some extra decimal places, because if you're going to round your final answer to 2 decimal places, you want any intermediate calculations you do with decimals to have more than 2 decimal places. In any case, I'm sticking with fractions for a little while longer, even though you don't have to. So the next thing I want to do is add up that new column that I just created. Of course, if you add a negative, it's like subtracting. So 105/54 minus 141/54 is negative 36/54. And now I'm going to change that to a decimal and round it to 2 decimal places. That comes out to be negative 0.67. So about 67-cent loss. So when this player plays this game over and over again, on the average, the player can expect to lose about 67 cents each time he plays this game with a $3 bet. Number 16. The probability that a 22-year-old female in the U.S. will die within 1 year is approximately 0.00044. If an insurance company sells a 1-year $30,000 life insurance policy to such a person for $75, what is the company's expectation? And round the answer to the nearest dollar. So, reading this very closely, you're selling a 1-year policy, or the company is, for $30,000 coverage at a cost of $75 to the person buying it, who is a 22-year-old female. If this 22-year-old female dies, the company loses $30,000. It's paid to that female's estate or to whoever that female designated as beneficiary of that policy. But it still keeps the $75 that the person paid to buy the policy. So technically, the company doesn't quite lose $30,000. The company loses $30,000 minus the $75 that the 22-year-old female paid for the policy. So really, the company only loses $29,925. It's not much, but it's important to getting an exact answer here that the company actually doesn't lose the entire $30,000 because of the premium payment. But if she doesn't die, the company gets that $75 free and clear. That's just profit. As usual with these expectation problems, we need to build a table. We need a column for the company's gain or loss. We're looking at this from the company's point of view, so it's the company's gain or loss, and then we need a probability column. And of course, the rows has to do with whether the female, 22-year-old female dies or doesn't die. If we can fill in that table, we're halfway there, or probably more than halfway there. As we said earlier, the company loses $29,925 if she dies in that 1 year period. So it's a negative $29,925. If she doesn't die, they make a profit of $75, which is the premium that she paid to get the policy. Now we need to calculate the probabilities. Well, not much to calculate. They really gave them to you. They knew that the probability that a 22-year-old female in the U.S. will die within a year is about 0.00044, so we can put that in. Well, the probability that she doesn't die then is 1 minus that. If you take 1 minus 0.00044, you get 0.99956. That's the other probability. Now you simply multiply across and then add down. If you multiply across the first row, remember that's a negative $29,925, so it's negative 13.167. And as I've said before, if you're rounding, you want to take more decimal places than you are going to round at the end. Since we're rounding to the nearest dollar, I'll probably take 2 or 3 decimal places. So I took 3 and got negative 13.167. If you multiply across the second row, you get 74.967. And if you add, again, adding a negative is like subtracting, and you'll get 6180. So the company, to the nearest dollar, can expect to make about $62 every time they sell a policy like that, which is their profit margin, which allows them to stay in business. Number 17. The probability that a 30-year-old male in the U.S. will die within 1 year is about 0.00142. An insurance company is preparing to sell a 30-year-old male a 1-year, $50,000 life insurance policy. How much should it charge for its premium in order to have a positive expectation for the policy? And once we get this answer, we want to round it to the nearest dollar. First of all, if he doesn't die, the company makes a profit of whatever the premium is. In the simpler problems, we knew the premium and we were calculating the expectation. But this time, they don't tell us the premium. And within the framework of the problem, we work it the same way, but since we don't know the premium, we'll have to use a variable for it. So I'll use P for premium. So if he doesn't die, the company makes P dollars. And our goal is to find out what P must be. We'll need to do a little algebra, but at the end, I'm going to show you a shortcut that gets you around the algebra if you'd like to use it. But for now, we're going to do some algebra to solve this problem. So we put in P instead of an actual number because we're looking to solve for P. Doesn't die, the company makes a profit of whatever that premium is, we're calling P dollars. But if he does die, the company loses that payout of $50,000 but keeps the premium, which we're calling P. So the company's actual loss is $50,000 minus whatever they took in from the premium, which we're calling P. So it'd be $50,000 minus P. We're going to build the table just as always. We need a column for the company's gain or loss. We need a column for the probability of that happening. And then we need to, on the rows, look at whether the 30-year-old male dies or doesn't die. And we've got to fill out that table. The probabilities will come later, but right now we've already decided that if he dies, the company is going to lose, which means it's a negative. The company is going to lose $50,000 minus P. But it's negative, so we need parentheses around that entire 50,000 minus P. But if he doesn't die, they make a profit of whatever the premium is, which we're calling P. Now, what are these probabilities? The probability is given in the problem of dying for a 30-year-old male in the U.S. of being 0.00142, meaning that the probability he doesn't die is 1 minus that. If you take 1 minus 0.00142, you get 0.99858. So that's the probability that this 30-year-old male in the U.S. doesn't die. Once you get the table, you multiply across, being careful about your signs, and then you add. So if I multiply a negative times a positive, I know I'm going to get a negative answer, so I went ahead and put a negative sign out there. And then I just take the product of 0.00142 and 50,000 minus P. And on the second row, I just get P times 0.99858. So I get 0.99858P. I need to add those together. I went ahead and multiplied through by the parentheses on top. So I first have to take negative 0.00142 times 50,000, and that gives me a negative product. But then I take negative 0.00142 and multiply by negative P, which makes it a positive. So I get positive 0.00142P. And then, of course, I have to add that to the product from the second row, which was 0.99858P. And if I want the expectation to be positive. 0 is where a number changes from positive to negative. So I want to set it equal to 0, and I know that anything more than that will be a positive expectation. So if I set it equal to 0 and solve, it turns out that if I take negative 0.00142 and multiply by 50,000, I get negative 61. And if I take 0.00142p and add 0.99858p, I get just p. I get 1p. So if I add a 71 to both sides, I'll find out that the premium needs to be set at least $71 for the company to make a profit. In other words, 71 is the break even. Anything higher than that will be a profit. Anything less than that will be a loss. I did promise you a shortcut, so I'll show it to you now. There is a way to avoid all that algebra if you would like to, and that comes with noticing something. My so-called shortcut comes from noticing that down below, when I added 0.00142 and 0.99858, it added up to exactly 1, which gave me a 1p, or just p. That was not a coincidence. So that's my shortcut. It always happens. It's not a coincidence. So what that tells me is, since those two numbers always add up to 1, I just got to figure out how that 71 came in, or that negative 71. Well, it came from taking 50,000 and multiplying it by 0.00142. That's where the negative 71 when it was on the left side, or the 71 when you moved it back over, came from. So it turns out that I can just take the value of the insurance policy, which in this case is $50,000, and multiply it by the probability, and that will give me the answer without doing any algebra. In other words, I could have just looked and said, well, 50,000 times 0.00142 is $71, and it would have avoided the entire thing, really, not just the algebra, but even the setup of the table. So that shortcut is really nice if you want to use it. But it is also sort of nice to see why the shortcut works. 18. A construction company has been hired to build a custom home. The builder estimates the probabilities of potential profit or loss is shown in the table below. What is the profit expectation for the company? So this table gives us a profit and loss amount column, and it gives us a probability. As I've said before, this is the easiest setup for an expectation. All you have to do is multiply across, which I've done here, and then add them up. So if you take the products across, 20,000, 21,000, 7,500, 0, negative 1,600, and negative 800, add them up, you get 46,100. And that is a positive number, so that's the expected profit for this construction company. Number 19, find the mean, median, and the mode or modes, if any, for the given data. Round non-integer means to the nearest tenth, and if there's more than one mode, enter your answer as a comma-separated list. If an answer does not exist, enter DNE for does not exist. So our numbers are 20, 26, 15, 18, 32, 23, 10, and 24, and we want to calculate the mean. Remember, when you calculate the mean, you're going to make sure that you don't have anything stuck in the calculator's memory already, so I press on. That sort of clears everything. Mode dot or mode period, whatever you want to call that symbol, puts you into stats mode. Once you're in stats mode, you need to type in the data followed by the M plus key. So you put 20 M plus, 26 M plus, 15 M plus, 18 M plus, 32 M plus, 23 M plus, 10 M plus, 24 M plus. Students often miss that last M plus, but if you don't press that last M plus, the 24 doesn't go in and you're going to get the wrong answer. And when you've gotten all the data in, you hit Shift 7, which calculates the mean. And if you do that, you'll find out that the mean is 21. Moving on to the median, you have to put the numbers in order to get the median. Well, if you order the numbers, you get 10, 15, 18, 20, 23, 24, 26, and 32. The median is the middle number of the group, and if there is no single middle number, you take the two that are in the middle and average them. Well, the two in the middle in this case are 20 and 23, and if you add them up and divide by 2, you end up with 21.5. That's the median. Finally, let's move on to the mode. The mode is the number that appears the most frequently. In this case, there's not a single number that appears more frequently than any other number, so we say there is no mode, and the problem said if the answer doesn't exist, you put in D and E. Number 20. In some 4.0 grading systems, a student's grade point average, or GPA, is calculated by assigning letter grades to the following numerical values. I won't read them all, but for example, an A is a 4.00, a C minus is a 1.67, and a D minus is 0.67. Anyway, you can see those for yourself. The instruction is to use this grading system to find this student's GPA and round to the nearest hundred. So you can see Jerry's grades for the fall semester. He made an A in English in a 3-credit-hour course. He made an A minus in anthropology in a 3-credit-hour course. He made a B in chemistry in a 4-credit-hour course. He made a C in French in a 3-credit-hour course. And finally, he made a B minus in theater in a 2-credit-hour course. You have to get rid of those letter grades and change them to their numerical values. And this is a weighted average because all the courses don't count the same number of credit hours. If every course counted the same credit hours, you could just average the numerical values and be done with it. But anytime one value is weighted differently than another value, you have to use the weighted average technique. So you want to first change all those course grades to their numerical values. The A becomes a 4.00, the A minus becomes a 3.67, the B becomes a 3.00, the C becomes a 2.00, and the B minus becomes a 2.67. I'm just going to copy the course units back beside it. Those are the weights. The credit hours for those courses are the weights. A bigger course unit value means that grade should count more. Once you do that, you want to create a products column, just as we've done before. Multiply across. Then you want to get the sum of those last two columns. It really doesn't matter what order you do them in, but let's just go ahead and do the weights column first. 3 plus 3 plus 4 plus 3 plus 2 is 15. We also need the sum of the products column. If you add those up, you'll find out that's 46.35. And the GPA is simply the sum of the products divided by the sum of the weights. That's 46.35 divided by 15, which gives you 3.09 for the GPA. And doing it this way accounts for the fact that not all the courses are worth the same number of credit hours. Number 21. A professor grades students on 4 tests, a term paper, and a final exam. Each test counts as 15% of the course grade. The term paper counts as 20% of the course grade. The final exam counts as 20% of the course grade. Alan has test scores of 90, 76, 80, and 92. Alan received an 84 on his term paper. His final exam score was 92. Use the weighted mean formula to find Alan's average for the course and round the answer to 1 decimal place. First of all, you need a column for the grades. Those are the values that you're trying to calculate an average for. Then you got to realize that all the grades don't count equally, which is what makes it a weighted average. So the weights are the percentages that each count. So the 90 is one of the test scores, so it counts 15%. So is the 76, so is the 80, so is the 92. The 84 is the term paper grade, which is 20%, and the 92 is the final exam score, which is also 20%. Once you get the weights, then you create a products column and multiply. If you make all those products, you'll eventually need to add up the weights and add up the products. It doesn't really matter which one you do first. If you add up the weights, you get 15 plus 15 plus 15 plus 15 plus 20 plus 20. That's 100. If you add up the products, you get 859. Now to get the final average for Alan, you take the sum of the products and divide by the sum of the weights, and that comes out to be 85.9. So Alan's course average is 85.9. 22. Find the mean, median, and all modes for the data given in the frequency distribution. Round your answers to one decimal place, and if there's more than one mode, enter your answer as a comma-separated list. If an answer doesn't exist, use DNE. So these are points scored by Lynn. The first column are the actual points in a basketball game, and the second column tells how often that happens. That's the frequencies of that particular score. So Lynn scored 3 points 10 times, 6 points 9 times, 8 points 10 times, 9 points 8 times, 13 points 3 times, 18 points 6 times, and 22 points 3 times. Let's start out with the mean. Press on to clear out any old data. Mode dot gives you the stats mode that you need to calculate these. And then you want to put in the numbers. 3 goes in 10 times. So you type in 3, then you hit M plus 10 times. So you 3 and then do M plus 10 times. Then you move down to the 6. Type in 6 9 times. So you type in the 6 and hit M plus 9 times. Then you type in 8 and hit M plus 10 times. Then you move down and you type in 9 and hit M plus 8 times. Move down to the 13, so you enter 13 and press M plus 3 times. Move down to the 18, so you enter 18 and you press M plus 6 times. Finally, you move to the 22, so you enter 22 and you press M plus 3 times. After you've gotten all the data in, you do Shift 7 for the mean, and you'll get an answer of 9.163265. We want the answer rounded to one decimal place, so that would be 9.2. Then you move to the median. For the median, you have to look at these frequencies and figure out, if you put these numbers in order, which one will be in the middle. Well, think of it this way. You've got 3 written down 10 times, 6 written down 9 times, 8 written down 10 times, 9 written down 8 times, 13 written down 3 times, 18 written down 6 times, and 22 written down 3 times. If you add up the frequencies, you'll see that you have 49 numbers. You're trying to figure out which one is the middle. Well, 49 is an odd number, so that means that there's a single number in the middle, and 24 plus 24 is 48, so there must be 24 on the left, 24 on the right, and the median is the one in the middle, which means the median is the 25th number. So all you've got to do is go to that chart and figure out which one is the 25th number. So I'm going to go back to that chart. I know by the time I've written down 3 10 times, I've already got 10 numbers, and then if I write down 6 9 times, that's the 11th, 12th, 13th, 14th, 15th, 16th, 17th, 18th, 19th. Then I start writing down the 8 10 times, so that's the 20th through the 29th position. That's 10 of them. Well, I'm looking for the 25th one, so the 25th one must have been 8. So once I pass 25, I can stop. And since 25 was one of the 10 8s, I know that the median is an 8. To me, that's the easiest way to do it. You could actually write down all 48 of those numbers and put them in order, but you can really do it from the table by starting with the frequencies and count up until you get to whatever the median number is, the median position is, and then cross-reference and see what number you were writing down at that point. So the median is 8. Going to the mode, the 3 appears 10 times, as does the 8, so they're both the highest frequency, and it said to put them with commas between them if there's more than one. So there are actually 2 modes, 3 and 8. 23. Another measure of central tendency for a set of data is called the mid-range. The mid-range is defined as the value that is halfway between the minimum data value and the maximum data value. That is, the mid-range is the sum of the minimum and maximum values divided by 2. The mid-range is often stated as the average of a set of data in situations in which there are a large amount of data and the data are constantly changing. Many weather reports state the average daily temperature of a city as the mid-range of the temperatures achieved during that day. For instance, if the minimum daily temperature of a city was 60 and the maximum daily temperature was 90, then the mid-range of the temperatures is 60 plus 90 divided by 2, which comes out to be 150 divided by 2, which is 75 degrees. So after having defined mid-range, doing it is actually very easy. The problem says find the mid-range of the following daily temperatures which were recorded at 3-hour intervals. Round your answer to 1 decimal place. So you've got 59 degrees, 52 degrees, 73 degrees, 54 degrees, 75 degrees, 69 degrees, 53 degrees, 65 degrees, and 58 degrees. So to get the mid-range, you want the lowest and the highest added together, divide by 2. So the smallest is 52 degrees, the largest is 75, so the mid-range is just the sum of 52 and 75 divided by 2, and that comes out to be 63.5 degrees. Number 24. For the first half of a baseball season, a player had 86 hits out of 272 times at bat. The player's batting average was 86 divided by 272, which is about 0.316. During the second half of the season, the player had 64 hits out of 281 times at bat, and that batting average came out to, when you divide 64 by 281, to be about 0.228. What is the average mean of 0.316 and 0.228? That's just a straight mean. It says just to take the average of those two numbers. That just means you add them up and divide by 2. If you add up 0.316 and 0.228, you get 0.544. If you divide that by 2, you get 0.272. It does say to round your answers to 3 decimal places, and that's what we've got. So just the straight average is 0.272. Keep in mind, though, the player batted 272 times in the first half of the season and 281 times in the second half of the season. So that average is not a true measure because the more at bats should get weighted more. So the B part says, what is the player's batting average for the complete season? That's taking into account that the calculation we just did in A really is not reflective of what it should be because of the difference in the number of times at bat. In other words, the weights are different. Anytime the weights are different for values, you need to do a weighted average. So that's what part B is getting at. It's a weighted average. The values are the batting averages, and the number of times at bat are the weights. In the first half of the season, there are a different number of times at bat than at the second half of the season. So we build our table as usual. The batting averages, as I said, are the values. That's for the first half of the season, 0.316, and for the second half of the season, 0.228. The times at bats are the weights. In the first half of the season, the player batted 272 times. In the second half of the season, the player batted 281 times. And of course, as always, you make a products column, multiply across, you'll get 85.952 in the first product, and you'll get 64.068 for the second product. You're going to add up the weights and the products. It doesn't matter which you do first. I went ahead and summed the weights here first. 272 plus 281 is 553. Now summing the products, you get 85.952 plus 64.068, and that comes out to 150.02. And as usual, the average is simply the sum of the products over the sum of the weights. That's 150.02 divided by 553, which comes out to be 0.271. So a truer measure of the player's batting average for the complete season would be 0.271. That's more reflective of his real batting average for the season because you're taking into account that he batted different numbers of times in each half of the season. The final part says, does the answer in part A equal the average in part B? And the answer is no. You can see that A is 0.272 and B is 0.271. So no, they do not. Number 25. During a 12-hour period, the temperature in a city dropped from a high of 68 degrees Fahrenheit to a low of negative 23 degrees Fahrenheit. What was the range of temperatures during this period? Remember, the range is just the largest minus the smallest. So the largest temperature was 68. The lowest was negative 23, but you're subtracting a negative. That means it's like adding. So you get 68 plus 23, which is 91. So the range of the temperatures during this period was 91 degrees. Number 26. During a 2-hour period, the temperature in the city dropped from a high of 55 degrees Fahrenheit to a low of negative 11 degrees Fahrenheit. What was the range of temperatures during this period? Again, the range is just the largest value minus the smallest value. The largest, which is the high, was 55. The smallest, which was the low, was negative 11. But when you subtract a negative, it's like adding. So you get 55 plus 11, which is 66 degrees. 27. Find the range, standard deviation, and the variance for the given samples, and round the non-integer results to the nearest tenth. The data is 4, 5, 8, 11, 15, 16, 21. So the first thing you got to remember is this is a sample. In any case, the range is simply the largest minus the smallest. The largest value was 21, the smallest value was 4. The difference is 17, so the range is 17. The standard deviation for a sample, I told you the sample made a difference. It doesn't make a difference in the range, but it does make a difference in the standard deviation and variance. You want to clear everything out of the old memory, so you want to press on. That makes sure everything is cleared out. I usually press on key several times. Mode dot puts you into stats mode, and then you enter the data. 4M plus, 5M plus, 8M plus, 11M plus, 15M plus, 16M plus, and 21M plus. That's the way you enter the data no matter what you're doing. If you're doing the mean or the standard deviation variance, the data goes in exactly the same way. But if you want the sample standard deviation, you do shift 9. The only time you do shift 9 is if it's from a sample. This is from a sample, so you do shift 9, and that gives you 6.24118, and they ask you to round to the nearest tenth, so that'd be 6.2. The variance in this case is a sample variance, and the sample variance is just the square of the sample standard deviation, but you want to take the square of the unrounded value. So you go back to the 6.24118, not the 6.2. Square the unrounded value, you'll get about 38.9523, and then round to the nearest tenth, which would take you up to 39.0. 28. Find the range, the standard deviation, and the variance for the given samples. Round non-integer results to the nearest tenth. Again, this is a sample, so you keep that in mind. It matters. The data is 1.8, 2.1, 2.7, 2, 3.4, 3.6. Anyway, the range is always the largest minus the smallest. The largest value was 3.6, the smallest was 1.8, so the range is 1.8. This is a sample standard deviation. You enter the values the same as you always do. Pressing on a couple of times convinces you that you've cleared out all old data. Mode dot puts you into stats mode, and then you enter 1.8 by pressing M plus, 2.1 by pressing M plus, 2.7 M plus, 2 M plus, 3.4 M plus, 3.6 M plus. Once the data's in, shift 9 if it's a sample standard deviation, and it is here, and that gives you 0.761577. They want it rounded to the nearest tenth. That'd be 0.8. The variance, in this case a sample variance, is just the square of the sample standard deviation, but you want to use the unrounded version, not the rounded version. So you want to square 0.761577 and then round it, and then it comes out to about 0.58, and if you do it to the nearest tenth, that would go up to 0.6. 29. The fuel efficiency in miles per gallon of small utility trucks was measured. The results are recorded in the table below. So you've got MPGs of 23, 25, 22, 26, 16, 24, 25, 31, 23, 21, 25, and 22. The instructions are to find the mean and sample standard deviation of these data. Round to the nearest hundredth. First of all, for the mean, or for any of these that you're going to use the calculator for, you need to get the data in. So you press on, that clears out any old data. Mode dot puts you into stats mode. Then you enter the data, followed by an M plus key. Do not forget to press M plus after entering the last data point, which is 22. If you don't enter that M plus that last time, the 22 won't go in. Once you enter that, though, if you want to do the mean, you do shift 7. And if you do shift 7, you get about 23.58333, and it's said to round your answers off to the nearest hundredth, so that would be 23.58. Now, when you get to the sample standard deviation, you've got to do shift 9. The data is already in there. You do not have to clear and put it back in again. If the data is still in there, unless you've cleared it, all you have to do is press shift 9. Shift 9 is the key combination to get sample standard deviation. So if you press that, you get about 3.528026, and rounding to the nearest hundredth, that would be 3.53. Number 30. A survey of 10 fast food restaurants noted the number of calories in a mid-sized hamburger. The results are given in the table below. Again, your data consists of calories. 513, 508, 503, 499, 497, 506, 459, 477, 463, and 515. The instructions are to find the mean and sample standard deviation of these data. Round to the nearest hundredth. So the mean, again, you have to get the data in. Pressing on clears anything old out of there. Mode, dot, make sure you're in stats mode. Then you enter every one of those data points followed by the M+ key. Again, don't forget to press M+ after that last 515. If you don't, that 515 didn't go in and your answer is off. Once you do that, shift 7 gives you the mean, and it turns out to be 494.00. It said to round to the nearest hundredth, so there you go, 494.00. Sample standard deviation, if the data is still in there, if you have not cleared it, you do not have to re-enter the data. Just press shift 9, which is the key combination for sample standard deviation, and that will give you about 20.3633658, and if you round that to the hundredth, that would be 20.36.